Printable Science presents a 3D printed Borescope mount for the optical bed leveling of your printer. One of the first things you'll be doing with a new printer, whether you built it from a kit or bought it fully assembled, is leveling your print bed. Auto bed leveling is becoming more common in 3D printers, but it's still a feature of more expensive machines. And well, there's bed leveling and there's bed leveling. While some auto leveling machines are totally automatic, not all are. So even if your printer boasts auto leveling, if there's any mention of sticking something between your bed and your hot end, then you're going to need to do some bed leveling, and this video is for you. Now, as you probably know, having a level bed is all about ensuring that you're laying down a good first layer, and having a good first layer is one of the essential components of generating successful prints. Unfortunately, leveling is a loathsome, time-consuming chore, only made worse by the fact that it needs to be done more than once, and it's a maintenance task that needs to be performed a lot more often than you'd like. Now, even though it's called bed leveling, to be accurate, the operation is actually called trammeling, which, as all you scholars out there know, is the gerund of the noun trammel, which comes from the 13th century French word tramel, which in turn comes from the ancient Latin word tramaculum, which means a three-layered fishnet. Well, there is a definition of trammel somewhere that's got nothing to do with fishing and more to do with binding or restricting movement. Okay, I get it. Maybe it makes sense then. Anyway, in the context of a 3D printer, what we need to do is adjust the slant or tilt of a bed such that wherever the extruder is, the build plate is bound or restricted to exactly the same vertical distance away from the extruder tip. Technically, leveling would imply making the printer bed level to the ground, and we'd use a level to do that. But given that the bed doesn't have to be level in order for a 3D printer to work, calling it bed leveling is a bit misleading. In fact, you can even run a lot of printers upside down, as demonstrated in this short clip from Electroboom's video, What's a Delta 3D Printer?
In fact, I should be able to print upside down too, I suppose. So let's just print upside down and see what happens. Well, good luck, printer. Well, I'll be. This printer can print upside down.
If you take the time to watch the full video, you'll see that Mehdi has mixed results, although I think he manages to get through the whole video without hurting himself. Anyway, while the print bed doesn't need to be level with the ground, the extruder needs to be the same distance from the print bed, regardless of where it's positioned on the XY plane. The basic principle is straightforward. You typically have a spring-loaded bed with either 3 or 4 anchoring bolts. Loosening the bolt raises that quadrant of the print bed and brings it closer to the extruder. Tightening lowers the bed and moves it further away from the extruder. Now, the trigonometry of the operation is such that you really only need 3 bolts, but because most people find the 3-point suspension confusing, and well, because it is trigonometry, most machines opt for 4 points, 1 in each corner of the bed. To help you with your trammeling, the printer manufacturer usually supplies a slip of plastic or paper or even thin metal. It's called a feeler gauge, and it has a specific thickness. The instructions are simple. You put the feeler gauge on the print bed and then you raise or lower the bed until you feel the right resistance when you pull on the feeler gauge. The instructions are not too loose and not too tight, or just until you feel a little resistance. Ever tried to tune a guitar? It's simple. You start by putting your finger on the 5th fret of the lowest string and pluck the string you are fretting, and then the next one highest. And then, and this is the magical part, if the 2nd string sounds lower than the 1st string, you tighten it with the tuning peg. And if it sounds higher than the 1st string, then you loosen it. And you keep on plucking and raising and lowering it until the 2 strings sound the same. But here's the deal. It doesn't really matter what you do. They never do sound the same. Or they always sound the same. Makes no sense at all. Okay, here are the facts. My lifelong ambition was to be the lead guitar player in a rock and roll band. Unfortunately, I could never tell when the strings sounded the same. So there you have it. 4 years of trying to learn how to play the guitar, and all I ever accomplished was learning that I couldn't tune a guitar. You know, that's why God invented electric guitar tuners. Now, I should have realized that I didn't need to feel limited by my inability to tune a guitar. I mean, we're talking about rock and roll here. Pete Townsend from the prehistoric British band The Who would regularly just smash his guitar in, no doubt, his frustration with tuning, as demonstrated by this ancient clip. But that's how it is with bed trammeling as well. It's magic. I have no idea what is meant by just a little resistance. And after a while, it doesn't seem like anything you do makes any difference anyway. You can get it to feel what you think is just right on one corner, only to discover you can't duplicate that just right feeling on any of the other corners. Magic, plain and simple. So for my part, I end up flushing away an hour of time and ending up with a bed that's probably more poorly trammeled than it was before I began. So at Printable Science, we came up with a different approach and made the whole process of bed trammeling, while not exactly fun, a lot easier and a lot less painful. The key is that we're going to make the whole process optical, and instead of relying on our sense of touch or on our sense of tug, we're going to use our eyes, and we'll be able to actually see what kind of gap we've got. To do this, we'll need what's known as a borescope, although they're most commonly sold under the name endoscope, but they're not endoscopes. An endoscope is an instrument that a surgeon shoves down your throat or up your butt to have a look around. But trust me, you don't want one of these things that are marketed as endoscopes shoved up your butt, unless you've got some spare cash for a surgeon to suture up a perforated intestine. Gosh, won't that be fun? Now, these borescopes go for as little as $6. One end plugs into the USB port of your computer, and the other end is a very small camera surrounded by some tiny LEDs to illuminate where the camera is pointing. What makes this a great choice for our given task is that the camera also magnifies the object it's pointed at, so you can see things much larger than you can with the naked eye. So the heavy lifting is done by the borescope, but we're also going to take advantage of the optics of the human eye. Unaided, without any magnification, the human eye can resolve a distance of about 40 microns. Given the magnification we're adding with the borescope lens, we're more likely to be able to resolve a gap much smaller than that. However, our borescope is not up to the task as it comes, out of the box. First of all, the camera is enclosed in a cylinder, and if you put that on a print bed, it'll just roll around. For our purposes, we want the horizon of the lens to always be parallel to the bed surface. Secondly, we need to accommodate the borescope camera's focal length. Any object placed closer to the lens than the focal length is going to be blurred and out of focus. And lastly, we want to provide an optical target to provide us with a reference to the current distance between the tip of the extruder and the bed. Now, fortunately, the design criteria can be met fairly easily, and at Printable Science, we put together a very, very simple mount for one of these borescopes in order to address the shortcomings of it as it's supplied. Our mount has 3 features. The first is an open cylinder which holds the borescope so that it fits snugly, because we don't want the borescope to rotate or move back and forth unless we specifically adjust it for that purpose. We chose the most common borescope diameter of 8 millimeters for our mount, but if you're one of our Patreon supporters, you should drop by our Patreon page and see how you can download a variety of other diameters to suit the borescope you have. Now, if you don't have a borescope yet and you're considering buying one, you'll want to avoid ones that have a stiff cable. The more flexible the cable is, the better. And also, you don't need a long cable. Even a meter long should meet most needs depending on the distance from your computer to your printer. A cable that's too long just gets in the way. Plus, you want to make sure that you get as many megapixels as possible. At the time this video was made, that seems to be about 2 megapixels, but if something bigger is available when you're shopping, go for that. On our mount, we extended the front edge to be as long as the focal length of the typical borescope, about 40 millimeters, so that when our borescope is positioned in the holder, it's precisely focused to the end tip of our mount. At the end of our mount, we have a single Z-layer pad, and we'll talk about that in a bit. This mount was printed with a 0.4 millimeter extruder diameter, 20% infill, 2 perimeters, 3 solid bottom and 3 solid top layers, and a Z or Z layer of 0.2 millimeters. While there could be some overhang concerns with respect to the top of the enclosing cylinder, the gap at the top of the cylinder removes the problematic angles, and anyway, we're not looking for great precision or quality here. We're just looking to produce a clip that can hold a borescope fairly snugly, while still allowing for some movement so we can adjust the positioning of the borescope in the mount. For reasons I'll cover shortly, you should choose a darker filament, or at least one that isn't too shiny. Although if you can't avoid a shiny filament and it causes problems later on, you can always apply some matte spray to your mount. As far as the filament type is concerned, this mount was just printed in PLA, but any non-flexible filament type you can run successfully on your printer should do. Once printed, you can insert the borescope in the mount, plug it into a computer or cell phone, and then launch an imaging program like Photo Booth on the Mac. Now we just rotate the borescope until the image is level and right side up, and finally we push or pull the borescope until the image on our screen is focused on the very end of the mount. It's often helpful to have a target to help you with focusing, and I most often use a ruler's edge. At this point, you'll want to adjust the lighting. Too bright and you'll experience washout, and too much glare. The problem with glare is why you should try and avoid bright, shiny filament. Now, once the lighting is set, check out the tip of your extruder to make sure it's clean. There's often a little blob of filament poking out the end, which needs to be cleared off. That's a simple process, although there's different approaches. Some manufacturers recommend you try and pull these blobs off with tweezers, but that's too finicky for me. I have one of these wire brushes that you can pick up for a couple of dollars at a hardware store. Just make sure the bristles are brass and not steel. Brass is the same material your extruder is usually made of, and brass bristles avoid the risk of gouging up the end of your nozzle. Once the extruder has been heated up, it just takes a swipe or two of the brush to get the blob of filament off, and you're done. Then just turn off the extruder heat and wait for things to cool down. And while we're on the topic, let's review the debate on whether or not you need to trammel your printer while your bed and extruder are at printing temperature. My vote is it doesn't really matter for machines that cost less than $100,000. Much is made of the precision of 3D printers, but in practical use, consumer-level FM printers really aren't that precise or that accurate. And anyway, if you've got a build plate or extruder that experiences serious enough dimensional changes between its cold and hot running state, so much so that it affects your prints, then you really need to get a better build plate, or a better extruder, or a better printer. Now, if you've removed any crud from the tip of your extruder and you've let your hot end cool down, you can move the print head into position with the home command, which is typically available from the printer menu. Your printer may have a custom menu selection for level bed, in which case you would choose that. Now, at this point, you'll probably want to turn your printer off as well. Often when a 3D printer is turned on, the motors are energized, which means you can't manually push around the extruder or bed, which we need to do in order to adjust our gap. Now, as you can see, this particular printer we're working with is a 4-bolt model. And we tighten or loosen them with a hex wrench that slips into the hole on the top of the screw. Common wisdom is to set your extruder print bed gap to about 2/3 of your first layer height, which for 200 micron stepping means we want a gap of about 150 microns. But before you get all panicky with these precision numbers, you need to appreciate that the single most important objective is to set the bed so that the tip of the extruder is exactly the same vertical distance from the print bed in all four corners. Within reason, it doesn't matter what the size of that gap is, as long as the gap is the same in all the corners. Now, this particular printer says the gap should be 0.05 millimeters, but we're probably going to end up setting it around somewhere around 2 millimeters. Now, the reason it doesn't matter what the size of the gap is that you can direct your slicer or modify your G-code to move the extruder to a Z starting point anywhere you like. You cannot, however, change the slant of your print bed on the go. So if we were to set our gap at, say, 1.1 millimeters, and the printer we were using specifies that the gap should be 0.05 millimeters, then we only need to set our slicer or add a line of G-code to our file that says, move the print head down 1.05 millimeters before you start printing. Indeed, some printers allow you to set that Z or Z adjustment or origin on the printer itself, so it's stored in the firmware of the printer. Now, the only way in which this may affect you is that you probably won't be able to print any of the canned demo models that come loaded on your printer's firmware. But that's a small price to pay for being able to properly trammel your printer so that you can print all other objects with ease. The one caution is that you need to ensure that you never set the gap so small that when the printer starts printing, it drives the extruder into the build plate, defaces your bed material, breaks your glass, or tears up your masking tape. So what you want to make sure is that that little pad at the end of our Borescope mount is at least as thick as the thickness gauge that your printer was supplied with, or that it is at least as thick as the specification for what the distance between your extruder and the bed should be in the home position. Don't leave this to chance, because you need to be aware that the home position is not necessarily the print start position. As long as the gap you are setting is higher than the thickness specified your printer, then you're going to stay out of trouble. So if you put your printer in the home position and it didn't move the extruder to one of the corners of the bed, you can gently push it to one of the corners. I typically start with the front left one. Then we can look at our Borescope and look at the gap between the extruder and the bed at that position. We need to ensure that the gap between the bed and the extruder is just high enough to let the pad slip between them. And here's where our sense of sight takes over from our sense of tug. We adjust the height of the print bed so that we can just detect the smallest amount of space or light between the tip of the extruder and the pad on our mount. When we've done that, we know that at that point our extruder is the height of the pad on our mount and that we're enjoying a precision of about 0.01 of a millimeter. The particular printer we're working with here is kind of annoying in that when the extruder is in the correct position over the corner of the bed, it actually obscures the head of the bolt. So we have to move the extruder out of the way to perform the adjustment and then move it back to see if we ended up where we wanted to be. Anyway, once we've fiddled around a bit and we've adjusted the gap so we can see the smallest bit of light shining through between our pad and the extruder tip, then we've adjusted that corner to the right spacing and we can proceed and set the other three corners to match it. I'm going to adjust the other three corners with time lapse so you don't need to take a nap waiting for me to get it all done. Okay, I've adjusted the gap for each of the four corners, but unfortunately we're not done just yet. That's because the bed pivots on 4 different points, and adjusting one point directly affects the level of the bed at the other points. So I need to continue inspecting and adjusting the gap in each corner until I get through a complete cycle of 4 bolts where the gap is the same at each corner. So back to time lapse, so we'll go while I go around the corners making sure that I get through a complete rotation with the gap correctly set at each point. Okay, there you have it. A complete inspection of our last 4 corners revealed a gap that was equal at each point, so now this printer is properly trammeled and the bed is level. In our next video in this playlist, we'll talk about how to adjust your slicer, printer firmware, or G-code to incorporate the required Z-layer compensation. Thanks for watching, and we hope that this trammeling video has been of use to you. and that you find that the optical method is a vast improvement over the friction fit of the feeler gauge, and that our Borescope mount becomes one of your go-to tools when adjusting your printer. Please leave comments and questions below. And if you enjoyed this video, please click the thumbs up button. And you can help us by showing your support by clicking the subscribe button down below. And you may want to click the notify bell as well, as we're going to be releasing a number of valuable videos on how to calibrate your printer with incredible precision. And please consider supporting Printable Science on Patreon using the link below. Being a Patreon supporter provides you with lots of extras and additional information, as well as going a long way to defray the cost of making these files and videos. Down below, you can also get the link to where you can download a copy of the STL file of the mount from Thingiverse, so you can print your own copy. As always, you can also download a copy of the STL file for this and other projects directly from our website. The latest files, a discussion board on trammeling, and our Borescope mount are available at the printablescience.com website, where all the science that fits, we print.